Okay, let's go ahead and take a look at the practice that we usually do at the end of this. So here's what we got. According to the American Dental Association, 8% of adults have never had a cavity. A dental graduate student contacts a simple random sample of 1,000 adults and calculates the proportion p hat in the sample who have never had a cavity. What's the mean of the sampling distribution? Well, the mean of the sampling distribution, if we look at this, it's always going to be stated. We're going to go with this one right here. We're going to say that the mean of the sampling distribution, that's how we say that. The mean of the sampling distribution of p hat, mean of p hat, is going to be equal to the true proportion. So in this case, 0.08. We're going to draw the conclusion that the mean is what's claimed, 8%. Calculate and interpret the standard deviation of p hat. So here's the formula for the standard deviation of p hat. It is, and this is on our formula sheet. If we look on our formula sheet, it's right there, and I can show you on our formula sheet. If we go to page 2, right there's our formula for a standard deviation of sampling distribution of proportions, p times 1 minus p over n. So what I'm going to do, p times 1 minus p over n. So it's going to be the square root of 0.08 times 1 minus 0.08 over, in this case, the sampling, our sample size is going to be 1,000. And when we do that, we're going to get 0.00209. And what this basically says is that the sample proportion of adults that have never had cavity, adults that never had a cavity, varies, well, typically varies from the mean. And in this case, the mean is from the mean 0.08 by 0.009. So this says there's a little variability. So like when we go ahead and pull that out, we're going to be off by, less than 1% each time, but it is going to have some variability. Is the sampling distribution approximately normal? Okay, this is that tenet. This is going to be that rule where what we're going to do is we're going to do n times p, and we're going to do n times 1 minus p. We're going to count our successes. We're going to count our failures. So in this case, we're going to do 1,000 times 0.08. That's going to give me 80. We're going to do 1,000 times 1 minus 0.08. That's going to give me 920. Both of those numbers are greater than or equal to 10. So I know that the shape is approximately normal. So now what we're going to say is find the probability that the random sample result of adults will give results within 2 percentage points of the true mean. So if we're looking at this one right here, what we're saying is the following. We got our curve here. In our middle, we got 0.08. And what we would do is if we put the standard deviations down, go ahead and show you 0.08 plus 0.009. So this is going to give me 0.089 plus 0.009 plus 0.009. This is going to give me 0.098 plus 0.009. And this out here is going to give me 0.107. Now what I need to do is I need to subtract. So I'm going to do 0.08 minus 0.009. And that's going to give me 0.071 minus 0.009. It's going to give me 0.062. And last but not least, minus 0.009 is going to give me 0.053. And this thing says within 2. So within 2 is going to be between 6% and plus 2 is going to give me 10%. I want to know what's the probability I'm going to be in between here. What's the probability? And here's how you'd write it. 0.06 p hat 0.10. And what we're going to do is we're going to use Normalcdf. The arguments we're going to use is our lower bound is 0.06, our upper bound is 0.1, our mean is 0.08, our standard deviation is 0.09. So that's my lower bound, my upper bound, my mean, and my standard deviation. And we're going to break out the trusty calculator, second bars, Normalcdf, 0.06, 0.10, 0.08, 0.09. So 0.9737. So this probability is 0.9737. So if I did this, I'd be pretty darn confident that I'd find someone between 6 and 10% that were within that 8%, within 2 points of 8%. So last one, if the sample size were 9,000 instead of 1,000, how would this change the sampling? Well, again, what I'm saying is I'm making the sample size larger. It's not going to change my shape. My shape is unchanged. Nothing. Very rarely am I going to change the shape when I'm doing a constant because I'm multiplying by a 9. The center, I'm telling you right now, center is not going to change. It's still going to be 8%. What is going to happen is all of a sudden, because to do this formula, notice mean has nothing to do with sample size. Standard deviation has everything to do with sample size. We are going to change this number and we're going to change it by multiplying it times 9. So what I'm saying is we have this as our original formula. We're going to multiply it by 9. If you actually do a little bit of the algebra here, you could go ahead and make it look like this. I took the numbers out, and this is going to be 1/3 as large the standard deviation. The standard deviation is going to be 1/3 as large. And that's a good trick to know, is that anytime you see a perfect square, since we're doing it underneath the radical, you take the square root of it. If it's making the sample size larger, it's going to shrink my standard deviation. If I'm making my sample size smaller, it's going to increase my standard deviation. So hopefully that helps.